Microporous crystalline adsorbents such as metal organic frameworks and zeolites have potential applications in a wide variety of mixture separations. Most commonly, the ideal adsorbed solution theory is used to describe mixture adsorption equilibrium. In this presentation, I discuss scenarios in which the mandates of the IAST are violated and the description of mixture adsorption equilibrium requires us to introduce activity coefficients quantifying the thermodynamic non-idealities. To begin the discussions on the RAST, the Real Adsorbed Solution Theory, we start with a recap of the basic tenets of the IAST. The description of the thermodynamics of mixture adsorption begins with the Gibbs adsorption equation, written in this form: A differential of pi equals the sum of the product of the molar loading of component I times the differential of the chemical potential of component I. A is the specific surface area, and pi is the spreading pressure within the units of newtons per meter. At thermodynamic equilibrium, the differential of the chemical potential of component I is related to the differential of the partial fugacity in the bulk of fluid phase by this expression. In the ideal adsorbed solution theory of Myers and Prausnitz, the partial fugacity of component I in the bulk fluid phase is related to the mole fraction of component I in the adsorbed phase by an expression that is the analog of the Raoult's law for vapor-liquid equilibrium. Pi superscript 0 represents the sorption pressure of species I, and the sorption pressures satisfy this expression that implies that the sorption pressures are such that the spreading pressure for mixture adsorption equals the spreading pressure of component 1 on its own and the spreading pressure of component 2. In these integrals, these represent the unary isotherms for component 1 and the unary isotherm for component 2. Since the surface area A is not easily accessible, it is convenient to define the surface potential phi as the spreading pressure times the specific area divided by RT. The surface potential can be determined from information on the unary isotherms. We summarize the key assumptions that are made in development of the IAST. All the adsorption sites within the microporous crystalline material are equally accessible to each of the guest molecules, and this implies there's a homogeneous distribution of guest adsorbates within the pore landscape. There's no segregation, no congregation, or preferential siting of guest molecules within the pore topology. And the specific surface area that is occupied by each molecule remains unchanged in mixture adsorption. To give just one example in which the mandates of the IAST are fully met, we consider the adsorption of mixtures of carbon dioxide and methane in MFI zeolite. MFI stands for mobile 5, consists of a set of intersecting channels. These are the straight channels that intersect the zigzag channels. There are 4 intersection sites per unit cell, and the channel dimensions are approximately 5.5 angstrom. The gas molecule CO2 and methane are uniformly distributed, and there are no preferential sites for either guest molecules within the pore landscape. This graph shows configurational-bias Monte Carlo simulations, CBMC, for unary isotherms of CO2, shown by the open circles, unary isotherm for methane, open squares, along with CBMC simulations for mixed adsorption, shown by the filled symbols. The red circles represent the component loadings for CO2 in the mixture, and the green squares represent the component loadings for methane in the mixture. The component loadings are compared at the same partial fluid phase fugacities in the bulk phase. We note that if we compare the component loadings for CO2 in the mixture with the unary CO2 loading, there is a reduction in the loadings of CO2 in the mixture when compared to the unary CO2 isotherm. The same is true for methane, but the reduction is significantly larger for methane because in the competitive adsorption, CO2 is preferentially adsorbed, and therefore the methane loading in the mixture is reduced to a significantly greater extent than the corresponding reduction for CO2. So this is a typical picture of competitive adsorption. The dashed lines are the IAST estimates of the component loadings in the mixture using the unary isotherm data fits. We note that the IAST provides an excellent description of mixture adsorption equilibrium. There's a further point to be made regarding the adsorption selectivity. The adsorption selectivity is defined as the ratio of the molar loadings to the ratio of the partial fugacities in the bulk fluid phase. And this expression may be rewritten in terms of the mole fractions, x1 and x2. And in view of this expression relating the partial fugacities and adsorption pressures and mole fractions, we write the adsorption selectivity of 1 with respect to 2 as the ratio of the adsorption pressure of 2 with respect to the adsorption pressure of 1. Now, for the thermodynamic equilibrium to hold, the adsorption pressures P10 and P20 yield the same value of the surface potential. And therefore, these expressions imply that the adsorption selectivity is uniquely determined by the surface potential irrespective of the compositions in the bulk fluid phase mixture. We shall test this conclusion using CBMC simulations of mixture adsorption equilibrium. In order to demonstrate that the adsorption selectivity for an ideal adsorbed mixture depends uniquely on the surface potential, we carried out CBMC simulations to determine the carbon dioxide methane adsorption selectivity in MFI zeolite for 4 different mixtures: a 50-50 binary CO2 methane mixture, a 20-30-50 CO2 methane nitrogen mixture, a ternary mixture 5-15-80 of CO2 methane and nitrogen, and a quaternary mixture of CO2 methane nitrogen hydrogen that is equimolar. For all 4 mixtures, the adsorption selectivity of the CO2 methane pair is uniquely determined by the ratio of the adsorption pressures of 2 to the adsorption pressure of component 1. And this ratio of adsorption pressures is uniquely determined by the surface potential. The IAST calculations are shown by the dashed lines, and the IAST calculations are in excellent agreement with the CBMC simulated adsorption selectivities for all 4 mixtures. We now highlight 4 different scenarios in which the mandates of the IAST are violated. We begin by looking at a scenario in which we have inhomogeneous distribution of guest molecules within the pore space due to preferential location of one of the guest molecules around the extra framework cations. In this case, we have sodium X zeolite. The CO2 molecule experiences strong electrostatic interactions with the extra framework cations, and they congregate around the sodium cations, leading to an inhomogeneous distribution of the guest molecules CO2, methane within the pore space. Due to this inhomogeneous distribution, the methane molecules faces a less stiffer competition with CO2 than would otherwise be the case if the guest molecules were homogeneously distributed. This gets reflected in the mixture adsorption equilibrium. In this graph, I present the component loadings against the partial fluid phase fugacities for both pure components, shown by the open symbols. Open circles are for CO2, open squares are for methane, and the fill symbols, the red circles, are for CO2 in the mixture, and the green squares are CO2 CH4 loadings in the mixture. The IAST anticipates a stiffer competition between CO2 and methane, leading to a lower loading of CH4 in the mixture than is realized in the CBMC simulations because of the inhomogeneous distribution of gas molecules. Due to the congregation of CO2 around the cations, the competition is less severe, and therefore the component loadings of methane calculated by CBMC simulations are higher than those calculated using the IAST. So the IAST fails at a quantitative level to describe precisely the component loadings, especially for methane in mixture adsorption. The second scenario in which we have a non-uniform distribution of adsorbates within the pore landscape is when we have preferential siting one of the gas molecules on certain locations. This is illustrated for mixtures of ethene and benzene in MFI zeolite, propene and benzene in MFI zeolite. The benzene guests prefer to locate at the channel intersections, whereas the linear ethene and propene molecules can locate anywhere within the pore space. Due to preferential locations of the benzene at the intersections, the competition faced by ethene and propene within the pore topology is lower than anticipated by the IAST. This graph plots the benzene alkene adsorption selectivity against the surface potential for binary mixtures of benzene and ethene, shown by the red circles, and the green squares represent the CBMC solutions for the adsorption selectivity for benzene propene mixtures. The dashed lines are the IAST estimates of the adsorption selectivity for both these mixtures. In both cases, the adsorption selectivity of benzene alkene mixtures is lower than anticipated by the IAST because the competition faced by the alkenes is lower than predicted by the IAST. Let's consider the purification of natural gas. Many reserves contain nitrogen up to 20%, whereas the pipeline specifications for natural gas demands that the nitrogen content be less than 3% because nitrogen lowers the heating value. Therefore, it is important for nitrogen removal for natural gas to selectively adsorb the nitrogen from natural gas, which is predominantly methane. However, most adsorbents are selective to methane that has the higher polarizability. In order to overcome this problem, the adsorbents that are chosen for nitrogen removal for natural gas rely on the principle of size exclusion. For example, ETS4, the pore sizes are adjusted to be about 3.7 angstrom, effectively rejecting methane from the pores, because the average diameter of a methane molecule is 3.8 angstrom. Due to size exclusion of methane, the pores of ETS4 have practically no methane present in it. Therefore, the competition between nitrogen and methane is practically non-existent. The IAST fails at a quantitative level to describe the mixture adsorption equilibrium, and this is demonstrated in the data presented in the thesis by Bardra. See also my paper in ACS Omega published in 2021. So when we have size exclusion of one of the gas molecules, then the IAST should be expected to fail. The same should hold for nitrogen methane adsorption in barium RPZ, where RPZ stands for reduced pore zeolite. The fourth scenario we consider, in which the IAST fails to provide a quantitative description of mixture adsorption equilibrium, is for water alcohol adsorption in zeolites and MOFs. I illustrate that for the case of water ethanol adsorption in DDR zeolite. DDR consists of cages of 278 cubic angstrom, and each cage is separated from an adjacent cage by windows that are approximately 4 angstrom in size. I plot here the radial distribution functions of OH distances between water molecules, ethanol molecules, and water ethanol molecules. We note that there is a sharp peak at a distance that is smaller than 2 angstrom, and that peak, this peak corresponds to the distance, OH distance, representative of hydrogen bonding. Particularly noteworthy is the strong peak in the water ethanol pairs of gas molecules. In other words, the water that is bound with the ethanol molecule gets adsorbed by riding piggyback, and this leads to an enhanced ingress of water into DDR zeolite. Due to a strong hydrogen bonding between water and ethanol molecules, the component loadings of water for mixture adsorption, shown by the red circles here, are significantly higher by about 1 to 1.5 orders of magnitude than the component loadings for pure water. This is the consequence of enhanced water ingress due to the fact that the water molecules are bound to ethanol molecules due to hydrogen bonding, and they ride piggyback on the ethanol and gets co-adsorbed with ethanol. This phenomenon, in which the component loadings in the mixture are higher than the pure component loadings compared to the same partial fluid phase fugacity, is called cooperative mixture adsorption. And this phenomenon is observed not only for DDR zeolite, but for chabazite, ziphate, faugisite, and LTA. And in this graph, I plot the enhancement in the water loading, that is the component loading for mixture adsorption, divided by the component loading for the corresponding unary system as a function of pore occupancy. And we note that the enhancement can be about 2 orders of magnitude depending on the pore occupancy. The IAST fails to capture quantitatively the enhancement in water loadings because the IAST does not cater for molecular clustering effects due to hydrogen bonding. In order to quantify the deviations from the ideal adsorbed solution theory for the 4 different scenarios highlighted in the foregoing slides, we need to introduce activity coefficients gamma I for each of the guest constituents. The introduction of activity coefficients into this expression results in the theory that is termed the Real Adsorbed Solution Theory. The sorption pressures are calculated in precisely the same manner as for the IAST. Indeed, the surface potential and the sorption pressures are the same as for the IAST calculations. For water ethanol mixture adsorption in DDR zeolite, the CBMC data for mixture adsorption can be used to determine the activity coefficients gamma 1 and gamma 2 for water and ethanol. These are plotted in this graph as a function of the surface potential phi. The surface potential phi serves as a proxy for the pore occupancies. At very low pore occupancies, the activity coefficients for either gas molecule reduces to unity, as is also evidenced by the CBMC data. The continuous solid lines are the parameters of a model for the activity coefficients. Specifically, we use here the Magul model with 3 parameters, A12, A21, and C. Particular attention needs to be paid to the incorporation of the factor 1 minus exponent minus C times phi. This factor ensures the right limiting behavior at low pore occupancies. Indeed, for phi tending to 0, this correction factor 1 minus exponent minus C times phi will tend to 0, and therefore the activity coefficients of both species should be unity. The three parameters can be determined by fitting the data on the activity coefficients, and based on the fitted model for the activity coefficients, we can determine the component loadings using the RAST, and these are shown by the continuous solid lines. It is to be expected that the RAST would match the component loadings determined from the CBMC simulations, because indeed the CBMC data have been used to back out these three model parameters. Now, there is no a priori method to determine the activity coefficients for mixtures in zeolites and MOFs, apart from the use of CBMC simulations. Experimental data on mixture adsorption and activity coefficients are rather scarce and quite limited, and therefore the use of the RAST relies heavily on estimations of the activity coefficients based on CBMC data. But such data are not always available, and for many cases the CBMC simulations are not accurate enough because the force fields are not reliable enough for determination of mixture adsorption equilibrium. I would like to leave the discussions on the RAST at this point and only summarize saying we can calculate activity coefficients required for the RAST model, provided we have data from molecular simulations on mixture adsorption.